Tonight, we're going to break down why up is one of the most misunderstood directions in space. On Earth, it's obvious. Gravity pulls you one way, and up is simply the other way. You've never had to think about it twice. But that certainty doesn't travel with you. Once you leave Earth, up is no longer defined by gravity pulling on you. It's defined by momentum working against you. The solar system is a flat disk, and everything inside it, every planet, every moon, every spacecraft ever launched, is moving along that plane, carried by motion that's been building since before any of it existed. Turning away from that plane means cancelling all of that motion first, before you can even begin to travel anywhere else. And trying to do that is one of the hardest, most punishing things physics could ever ask a spacecraft to do. By the end of tonight, you're going to understand where that disk came from, why it holds on the way it does, and just how much it takes to fight your way out of it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Right now, wherever you're sitting, you know exactly which way is up. You don't have to think about it. Your body feels it in the chair, in your feet, in the weight settling toward the floor. That feeling has one cause: Earth's gravity, pulling you toward its center. It's the most obvious, unquestioned thing in your entire daily experience. Every building you've ever walked into is built around that fact. Floors below, ceilings above. A single shared direction that everyone around you agrees on without a second thought. Now, take that feeling and try to bring it into space. It falls apart almost instantly. Astronauts on the International Space Station don't experience up or down in any meaningful way. They float. Modules on the station don't have a true ceiling or floor. They have a working orientation, chosen so the crew's brains have something consistent to hold on to. But it's arbitrary. You could flip the entire station upside down relative to Earth, and nothing would change for the people inside. There'd be no falling sensation, no correction needed, nothing at all. That's because the station isn't actually free of gravity. It's falling, constantly. The station and everyone in it are in a permanent state of free fall toward Earth. They're moving sideways, fast enough that they keep missing the ground, curving around the planet again and again. Free fall removes the sensation of weight entirely, and without weight, up and down stop meaning anything to your body. Astronauts describe a strange mental adjustment in the first days aboard the station, a kind of disorientation where their brain keeps hunting for a flaw that isn't really there. Most eventually settle on the module's visual layout as a working substitute. But the moment they float into a different module, oriented differently, the old sense of up can flip entirely, sometimes within seconds. This isn't just a curiosity about astronauts. It's a clue. It tells you that up and down were never really properties of space itself. They were always properties of gravity. Specifically, the gravity of whatever large body happens to be nearby. On Earth, that's Earth. Near the Moon, up points away from the Moon. Near Jupiter, up points away from Jupiter. There is no universal up written into the fabric of space. No cosmic ceiling, no cosmic floor. Every up is local, borrowed from whatever mass is closest and strongest. So the question, why can't you go up in the solar system, has to be rebuilt from scratch. If up isn't a fixed direction, what would going up out of the solar system even mean? To answer that, you have to look at the shape of the solar system itself. And it's not the shape most people picture. Most illustrations show the solar system as a loose cloud of planets scattered around the Sun in every direction. Almost like the Sun is the center of a sphere, with planets orbiting randomly around it. That picture is wrong. The real solar system is almost perfectly flat. Every major planet orbits the Sun in nearly the same plane. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, tilted from each other by only a few degrees at most. Earth's orbit defines what astronomers call the ecliptic, the reference plane most solar system geometry is measured against. Mercury's orbit is tilted about 7 degrees from that plane. That's the largest tilt of any major planet. And even that is a small wobble compared to how flat the rest of the system is. Venus is tilted about 3.4 degrees. Mars, about 1.8 degrees. Jupiter, Saturn, Uranus, and Neptune are all tilted by roughly 1 to 2 degrees. If you shrank the solar system down to the size of a dinner plate, the planets wouldn't just be sitting on the plate. They'd be riding along a surface so flat you could barely tell it wasn't a single sheet. This isn't a coincidence. And it isn't a design. It's a direct consequence of how the solar system formed. About 4.5 billion years ago, the Sun and everything orbiting it began as a single, roughly spherical cloud of gas and dust. A slowly rotating cloud with no particular flatness to it at all. That cloud had angular momentum, the physical property of rotation that resists being erased. As the cloud collapsed under its own gravity, that rotation didn't go away. It concentrated. Think of a figure skater pulling their arms in during a spin. The same amount of rotation packed into a smaller space means spinning faster. The collapsing cloud did the same thing, spinning faster and faster as it shrank, and a spinning cloud of gas naturally flattens. Any motion perpendicular to the spin gets cancelled out through countless particle collisions. Gas and dust colliding with other gas and dust, losing energy in every direction except the one aligned with the rotation. Over time, all of that material settled into a thin, rotating disk. A dense clump at the center eventually ignited into the Sun. Smaller clumps farther out became the planets. That disk is the reason the solar system is flat. The planets didn't choose to orbit in the same plane. They were born out of a spinning disk, and they simply kept the orientation that disk already had. This flat orientation even has an official name beyond the ecliptic. Astronomers call it the invariable plane. It's defined not just by Earth's orbit, but by the combined angular momentum of the entire solar system. Every planet, moon, and significant object weighted together. It's an extremely stable reference, barely shifting over millions of years. It represents the deep rotational memory of the disk the whole system was born from. Nearly everything of significant size in the solar system still respects that plane. The asteroid belt between Mars and Jupiter sits close to it. The larger, more organized parts of the Kuiper belt beyond Neptune sit close to it too. Even the rings of Saturn, Jupiter, Uranus, and Neptune sit in the plane of each planet's own equator, itself roughly aligned with the overall system. The solar system, at every scale, keeps returning to the same flat shape, the same shared direction of motion. That motion was baked in at the very beginning. Nothing since has had the energy to erase it. So now, the question sharpens. The solar system is essentially a flat disk, with the Sun at the center and the planets riding around it in nearly the same plane. That means up, in this context, means something specific. It means moving perpendicular to that disk, straight out of the plane, either above it or below it. away from where all the planets, moons, asteroids, and comets are lined up. It sounds like it should be easy. There's nothing physically blocking that direction. No planet in your way, no debris field, no wall. Empty space extends above and below the ecliptic, exactly as it does within it. And yet, in more than 60 years of space exploration, humanity has sent exactly one spacecraft on a mission specifically designed to leave that plane and travel over the sun's poles. Everything else, every planetary probe, every lander, every flyby mission, every spacecraft currently leaving the solar system entirely, has stayed remarkably close to that same flat disk. The reason isn't a lack of imagination. It's physics. And it's brutal. To understand why, you have to think about what a spacecraft actually inherits the moment it leaves Earth. Earth isn't standing still. It's orbiting the Sun at an average speed of about 18.5 miles per second. That's more than 66,000 miles per hour. It's tearing around its orbit in the same plane as every other planet. Every spacecraft launched from Earth starts with that same sideways velocity built in. It was riding on a planet that already had it. You don't get to opt out of it. The moment your rocket clears the atmosphere, it's still carrying Earth's full orbital speed, moving sideways around the Sun at 18.5 miles per second, whether you asked for that speed or not. If your goal is to travel to another planet within the same plane, that inherited speed is a gift, something you build on rather than fight against. Mission planners use it constantly. They launch spacecraft in the direction of Earth's own motion to get a running start toward the outer solar system. But if your goal is to leave the plane entirely, to travel straight up or down relative to the disk, that same inherited speed becomes your biggest enemy. Here's why. Going up out of the ecliptic doesn't just mean adding a new upward push to your spacecraft. It means cancelling out the sideways push you already have. Imagine standing on a giant spinning merry-go-round, moving in a circle at high speed. Someone asks you to walk straight off the edge, directly away from the center, without any of that circular motion carrying you sideways as you go. You can't simply step off. Your body is already moving in a circle. Unless you shed that circular motion first, you'll go flying off at an angle, still carrying your sideways momentum with you. The only way to leave straight out is to first cancel the spin you already have. A spacecraft trying to leave the ecliptic plane faces exactly this problem. Except, instead of a merry-go-round, it's the entire solar system's orbital motion. 18.5 miles per second of sideways velocity that has to be cancelled before any meaningful upward or downward motion can even begin to dominate the spacecraft's path. Cancelling that velocity costs an enormous amount of energy. Engineers measure it in a value called delta V, the total change in velocity a spacecraft's engines have to provide over the course of a mission. To put numbers on it, escaping the Sun's gravity entirely from Earth's orbit requires roughly 7.9 miles per second of delta V beyond Earth's own orbital speed. That's a huge but achievable number. Missions like Voyager and New Horizons have actually pulled it off, using a combination of powerful rockets and gravity assists from other planets. But cancelling Earth's full 18.5 miles per second of sideways orbital velocity in order to travel straight out of the plane instead costs even more than that. You're not adding a small correction to an existing path. You're trying to erase almost the entire orbital speed the spacecraft was born with. Only after erasing it does traveling up out of the plane even become the dominant motion. In practical terms, a direct, brute force missions straight out of the ecliptic would require more raw propulsion than anything humanity has ever built a rocket, powerful enough to deliver in a single launch. Chemical rockets are the kind currently used for every crewed and uncrewed mission ever flown. They simply don't carry enough fuel to make that kind of maneuver directly and still have anything left over to actually do science once they get there. This is the heart of why going up in the solar system is so much harder than it sounds. It's not that the direction is blocked. It's that everything launched from Earth starts with a built-in sideways velocity so large that turning 90 degrees away from it is one of the most expensive maneuvers in orbital mechanics. More expensive, in raw energy terms, than leaving the solar system altogether in the direction you were already moving. So how did humanity manage to get close, even once? The answer is a mission called Ulysses, a joint project between NASA and the European Space Agency. It launched in October of 1990 from the Space Shuttle Discovery. Ulysses had one job that no other spacecraft before or since has attempted: fly over the sun's poles, above and below the ecliptic plane. Study the solar wind and the sun's magnetic environment from angles no instrument had ever observed before. Engineers immediately ran into the same wall every mission designer runs into. There was no rocket in existence capable of directly cancelling that much orbital velocity and still delivering a functioning spacecraft to a useful polar trajectory. So they didn't try to brute force it. They borrowed a trick that had already proven itself on missions traveling outward through the plane: a gravity assist. But used in a way nobody had used one before. Ulysses launched toward Jupiter, not to study Jupiter itself, but to use Jupiter's enormous gravity as a slingshot. As Ulysses approached the giant planet in February of 1992, Jupiter's gravity bent the spacecraft's path dramatically, not just speeding it up or redirecting it sideways the way most gravity assists do. It bent the trajectory up and out of the ecliptic plane entirely. The encounter threw Ulysses onto a path that would carry it dramatically out of the plane, far above the sun's north pole and, years later, far below its south pole. Not straight up. Not a full 90 degrees. But close enough to look down on the sun's poles from an angle nothing built before it had ever reached. Jupiter did what no rocket on Earth could have done economically. It provided a colossal, free push of gravitational energy, precisely angled to convert Ulysses's flat, in-plane motion into a steep, out-of-plane trajectory. Without that assist, the mission would have been essentially impossible with the technology of its era. With it, Ulysses became the only spacecraft in history to have a primary mission built entirely around leaving the ecliptic plane and studying the sun from high solar latitudes. It passed over the sun's poles multiple times during its extended operational life, which lasted far longer than planners originally expected. It kept sending back data until it was finally decommissioned in 2009. Ulysses's success actually proves the rule rather than breaking it. It didn't get out of the plane by brute engineering. It got out by borrowing gravity from the one planet massive enough to bend a spacecraft's path that dramatically. Even then, the mission had to spend years traveling outward, first just to reach Jupiter, before the real maneuver could even happen. No other mission has repeated that feat. Not because scientists lost interest in studying the sun's poles, because Ulysses already demonstrated just how narrow and expensive the path to doing it really is. There has been discussion for decades about a successor mission, one that would push even further out of the plane than Ulysses managed. But the same fundamental cost keeps showing up in every proposal. The energy required to cancel orbital velocity and travel truly perpendicular to the solar system's disk remains one of the single most expensive things you can ask a spacecraft to do. It's worth comparing Ulysses to the handful of missions that actually are leaving the solar system outright. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. The contrast tells you everything. All 5 of those spacecraft are headed away from the Sun, out past the orbits of the outer planets, and eventually into interstellar space. None of them are traveling straight up or down out of the ecliptic in any dramatic way. Voyager 1 does have some inclination relative to the plane. A modest angle picked up from its final gravity assist at Saturn in 1980. Mission planners deliberately bent its path upward to get a close flyby of Saturn's moon Titan. They sacrificed the option of continuing on to Uranus and Neptune in exchange for that one close look. That decision sent Voyager 1 climbing gradually above the ecliptic plane as it heads outward. But the angle is modest, only around 35 degrees relative to the plane. It was achieved gradually over decades of travel outward, not the steep, immediate departure Ulysses achieved using Jupiter. Voyager 2 stayed much closer to the plane. It continued on to visit Uranus and Neptune before heading outward at a shallower angle, dipping below the ecliptic by a smaller margin. Both Pioneer spacecraft and New Horizons, after its Pluto flyby, are similarly close to the plane. They're dominated by their outward motion rather than any dramatic vertical departure. Every one of these missions is, in the deepest sense, still traveling largely within the flat disk the solar system was born in. They're simply heading toward its outer edge rather than climbing away from it. There's a reason mission planners keep choosing this path, even when leaving the plane entirely might sound scientifically appealing. Staying within or close to the ecliptic lets a spacecraft use the built-in orbital motion it inherited from Earth as an asset instead of a liability. It lets missions use gravity assists from other planets, which mostly also orbit close to the same plane, to gain speed efficiently, planet after planet. Voyager 2 famously used a rare alignment of Jupiter, Saturn, Uranus, and Neptune in the late 1970s to visit all 4, using a fraction of the fuel a direct mission to each would have required. That kind of efficient, multi-planet gravity assist path only works because the planets share a plane. The moment a mission tries to leave that plane, it loses access to most of the planets that could otherwise offer a free boost. Most of them simply aren't up there to assist with anything. Jupiter is really the only planet massive enough and positioned usefully enough to bend a spacecraft's path dramatically out of the ecliptic. That's exactly why Ulysses had to route through it, and why any future polar solar mission almost certainly will too. All of this reframes the original question in a much more precise way. Going up in the solar system isn't physically forbidden. Nothing in the laws of physics prevents a spacecraft from traveling perpendicular to the ecliptic plane. What makes it so difficult is that everything about how spacecraft are launched, how they gain speed, and how they use the planets to save fuel is built around staying within the plane. The plane is where all the useful gravity, all the efficient trajectories, and nearly all of the solar system's mass actually live. Straying from it means giving up almost every trick that makes interplanetary travel affordable. It means replacing those tricks with a single, brutally expensive maneuver, cancelling out nearly the full orbital speed you started with. It's less like a locked door and more like trying to walk uphill against a current that every other path in the solar system happens to be flowing with. There's another layer to this, because up doesn't stop mattering once you're clear of the sun's immediate neighborhood. The entire solar system, the sun, and every planet orbiting it, is itself embedded in something much larger, the disk of the Milky Way galaxy. That disk has its own plane, its own version of up and down, entirely separate from the ecliptic. The galactic plane is defined by the flattened structure of the Milky Way itself. It's the same kind of rotating disk shape the solar system has, just enormously larger, containing hundreds of billions of stars instead of 8 planets. Our solar system's ecliptic plane is tilted relative to the galactic plane by roughly 60 degrees. A steep, almost sideways angle. That means the direction that counts as up out of our own solar system's disk isn't the same direction that counts as up out of the galaxy's disk. They're two completely different orientations, layered on top of each other, inherited from two entirely separate rotating systems that formed independently, one nested inside the other. The sun itself doesn't sit locked in place within the galactic plane either. It gently oscillates above and below it as it orbits the galactic center. A slow vertical bobbing motion caused by the combined gravity of the galaxy's disk pulling it back each time it drifts too far up or down. The oscillation has an estimated period of roughly 30 million years, from peak to peak. It carries the sun and everything orbiting it, including Earth, a few hundred light-years above the galactic plane, and then a few hundred light-years below it, over and over. A slow, vertical rhythm, layered on top of the sun's roughly 230 million-year orbit around the galactic center itself. We are, in that sense, always moving up and down relative to the galaxy, just so slowly, and on such an enormous timescale that nothing about daily life or even human history has ever noticed it happening. So even the galaxy doesn't offer a fixed, final answer to what up really means. It offers another local plane, another local up, defined by its own rotating disk, tilted against our solar system's own local plane, itself tilted against Earth's own spin axis. Layered orientation, inside orientation, each one only meaningful relative to the structure that produced it. Zoom out far enough, past the galaxy, into the vast scale of galaxy clusters and the cosmic web of filaments that connect them. Even the galaxy's plane stops mattering, replaced by whatever larger structure of matter happens to be nearby. There is no true, universal, up anywhere in the cosmos. Every up is borrowed, every up is local, and every up eventually gives way to a bigger structure with a different one. Bring that back down to the original, much smaller question. Why can't you just go up in the solar system? You can, technically. Nothing physically prevents it. But the up you'd be traveling toward isn't marked by any wall, any barrier, or any rule of physics that forbids it. It's marked by cost. The entire architecture of the solar system is built around staying within the plane. The flat disk it was born from, the shared orbital motion every planet still carries, the efficient gravity-assisted routes that make interplanetary travel even remotely affordable. All of it. Leaving it means giving up nearly everything that makes space travel practical. It means paying, in raw propulsion, for a maneuver so expensive that in over 60 years of spaceflight, only one mission has ever been built specifically to attempt it. And even that mission needed to borrow gravity from Jupiter to make it possible at all. Up isn't gone from the universe, and it never really was. It's just never once, at any scale, been free. Every direction we've ever called up was handed to us by whatever gravity happened to be nearby. First Earth's, defining the up you feel standing right now. Then the sun's disk, defining the up that costs more fuel than escaping the solar system outright. Then the galaxy's own tilted disk, defining an up so large it takes 30 million years just to complete one gentle rise and fall. None of them are permanent. None of them are universal. They're just the closest available answer, borrowed from whatever massive structure happens to be shaping the space around you at that particular scale. And once you understand that, the solar system stops looking like a random scatter of planets around a star. It starts looking like exactly what it is. A flat, spinning disk, inherited from the cloud that built it, with an up and a down that exist, technically, in every direction perpendicular to that disk, but that remain, in practice, some of the most expensive, least traveled directions in the entire solar system. There's a deeper layer to the free-fall problem worth understanding. It explains why astronauts don't just get used to weightlessness the way you'd get used to a new pair of shoes. Your sense of up and down doesn't come from a single sense. It comes from at least 3 different systems working together. They normally agree with each other so completely that you never notice them as separate things at all. Your inner ear contains small fluid-filled structures called the vestibular system, tiny hair cells that detect the pull of gravity and the motion of your head, constantly reporting which way is down based on how fluid shifts inside them. Your eyes provide a second, independent signal. They watch the horizon, the floor, the walls, anything with a visible orientation, and compare it against what your inner ear is reporting. And your body has a third system entirely. Pressure receptors in your feet, your joints, your muscles, quietly reporting where weight is pressing against you. On Earth, all 3 systems agree constantly. Feet feel pressure, eyes see a floor below, inner ear detects downward pull. Your brain stitches all of it into one seamless, unquestioned sense of orientation. In free fall, that agreement collapses. Your inner ear still detects motion, but the steady downward pull it depends on to define down simply isn't there anymore. Your feet feel no pressure, because there's nothing pulling you against a surface. Your eyes may see a floor, painted or built into a module for the crew's convenience. But that visual cue now has to do all the work the other 2 systems use to share. The result, especially in the first 2 or 3 days aboard a spacecraft, is a kind of low-grade sensory conflict. Many astronauts describe it as space sickness, a form of motion sickness caused not by movement itself, but by disagreement between systems that have never had to disagree before. Roughly half of all astronauts experience some degree of this during their first days in orbit. It typically fades as the brain gradually learns to trust the visual system almost entirely, quietly demoting the inner ear's confused signals in favor of whatever the eyes report. That adaptation is so effective that astronauts returning to Earth after long missions sometimes experience the opposite problem. A brief period of dizziness and disorientation, as their inner ear has to relearn how to matter again. This is a strange thing to sit with. The up and down you rely on every day of your life isn't a fact about the universe. It's a running agreement between 3 separate biological systems, tuned by millions of years of evolution to work in exactly one specific condition, standing on a large gravitating body with a consistent downward pull. Take that condition away, and up and down aren't just harder to determine. They stop being meaningfully different from any other direction at all. Humans understood something was strange about direction in the heavens long before anyone left the ground. Ancient skywatchers tracked the motion of the sun, moon, and visible planets across the sky, night after night. They noticed that everything seemed to move along roughly the same narrow band, a path we now call the zodiac, the visual projection of the ecliptic plane onto our night sky. They had no way of knowing why the sun, moon, and planets all seemed to travel along that same narrow strip rather than wandering freely across the entire sky. But they built entire calendar systems and navigational methods around the observation. Without ever knowing, they were staring directly at the edge, on view of a flat orbital disk, from a vantage point sitting inside it. It wasn't until the work of astronomers in the 1500s and 1600s that the true architecture of the solar system began to take shape. A sun-centered system with planets tracing nearly coplanar orbits around it, rather than Earth sitting fixed at the center of everything. Even then, it took centuries more before anyone understood why that flatness existed at all. Why the planets seemed to respect one shared plane, instead of scattering in every direction the way stars do across the night sky. The answer, angular momentum from a collapsing, rotating cloud, wouldn't be worked out in detail until the 1700s and 1800s. It wasn't confirmed by direct observation of other star systems actually forming until space telescopes in the late 1900s and 2000s captured images of young stars still surrounded by their own flattened, dusty disks, caught in the act of becoming solar systems of their own. Seeing those young disks directly, glowing rings of gas and dust wrapped around newborn stars light years away, confirmed something important. Our own solar system's flatness wasn't a fluke or a special case. It's simply what happens, almost universally, whenever a spinning cloud of gas collapses under its own gravity. The physics behind that flattening deserves a closer look. It explains not just why the planets share a plane, but why that plane is so remarkably thin and stable. Angular momentum is one of those quantities in physics that nature refuses to destroy. It can be transferred, redistributed, and reshaped. But the total amount in a closed system stays constant. The cloud that formed our solar system was rotating slowly, almost imperceptibly, spread out across a region of space vastly larger than the solar system is today. As gravity pulled that material inward, the same total rotation had to be preserved. Now packed into a much smaller volume, which meant the rotation had to speed up dramatically. The same principle behind a figure skater, spinning faster as they pull their arms toward their body. But speeding up the spin only explains why the cloud started rotating quickly. It doesn't, by itself, explain why the cloud flattened into a disk, rather than simply becoming a smaller, faster spinning sphere. The flattening comes from collisions. Inside the collapsing cloud, countless particles of gas and dust were moving in every direction. Not just along the plane of rotation, but above and below it too, on wildly varied paths. Collisions were happening constantly in that dense, collapsing cloud. Whenever two particles collided, their combined momentum had to average out. Motion, aligned with the overall rotation, reinforced itself because it was shared by nearly everything else in the cloud. Motion perpendicular to that rotation, drifting up or down out of the eventual plane, had no such reinforcement. Collisions steadily cancelled it out, particle by particle, transferring that vertical energy into heat that radiated away into space. Over thousands of years, this constant collisional damping ironed the cloud flat. The same way a handful of loose sand thrown into a spinning bowl eventually settles into a thin, even layer along the bottom, no matter how randomly it started out. What was left, once the vertical motion had been erased and only the shared rotational motion remained, was a thin, spinning disk, dense enough at its center to collapse further and ignite as the sun, with smaller clumps farther out, slowly gathering into the planets we know today. This is why the planets don't just happen to share a plane. They were never in a position to do anything else. Every planet condensed out of material that had already been flattened by countless collisions before the planets themselves ever existed. Their orbits inherited the disk's orientation, the way a child inherits handwriting habits from years of copying the same motion. Not because anyone chose it individually, because the entire environment they formed in only offered one direction to move in. Not every planet ended up with exactly the same tilt, though the small differences that do exist tell their own story. Mercury's 7-degree tilt relative to the ecliptic is thought to be a lingering result of the chaotic, collision-heavy environment closest to the Sun. Fewer other bodies existed there to smooth out any remaining irregularities through their own gravity. The gas giants, Jupiter and Saturn in particular, are tilted by less than 2 degrees. Remarkably flat, given their enormous size. Likely because their formation involved gathering huge amounts of gas directly from the smoothest, most settled part of the original disk. In the layer where collisional damping had already done most of its work, Pluto is no longer classified as a major planet, but remains one of the most interesting objects in the outer solar system. It breaks this pattern dramatically, orbiting at an inclination of about 17 degrees relative to the ecliptic. By far the steepest tilt of any well-known body in that region. That steep tilt is one of several clues that Pluto's orbital history involved more disruption and gravitational interaction, likely with Neptune, than the more settled orbits of the inner and outer planets. Even farther out, in the loosely defined region beyond Neptune, known as the Kuiper Belt, tilts become far more varied and far steeper. The dwarf planet Eris, discovered in 2005, orbits at an inclination of about 44 degrees relative to the ecliptic. It spends much of its enormous, elongated orbit well above or below the plane that the 8 major planets so carefully respect. Sedna, an even more distant object with one of the longest known orbital periods in the solar system, follows a path tilted about 12 degrees from the ecliptic. But it reaches such enormous distances from the Sun that even a modest angle carries it extraordinarily far above the plane at the outer edge of its orbit. These objects are a preview of something important. The closer you look at the solar system's outer edges, the less rigidly that original flat disk continues to apply. The more individual, chaotic histories start to dominate over the smooth, collision-damped order that shaped the inner planets billions of years ago. That breakdown becomes complete once you go far enough out to reach the Oort cloud, the most distant and least understood region, gravitationally bound to the Sun. Unlike the flat, disc-shaped Kuiper Belt, the Oort cloud is believed to be roughly spherical. A vast shell of icy bodies surrounding the entire solar system in every direction, above, below, and all around the ecliptic plane equally. Its existence is inferred rather than directly observed. It's based mainly on the orbits of long-period comets that occasionally fall inward toward the Sun from seemingly random directions in the sky. They arrive from every angle, rather than clustering near the ecliptic the way short-period comets from the Kuiper Belt do. That randomness is the key clue. If the Oort cloud were flattened like the inner solar system, comets originating from, it would tend to arrive from directions clustered near the ecliptic, the same way objects from the Kuiper belt do. Instead, they arrive from every direction almost equally. That's strong evidence that the Oort cloud itself has no preferred plane at all. It's spread in a great spherical shell that may extend out to somewhere between 5,000 and 100,000 astronomical units from the Sun, an almost incomprehensible distance compared to the 8 planets huddled close to the Sun within a tiny fraction of that range. In a strange way, the Oort cloud is the one place in the solar system where up genuinely stops meaning anything special. Not because it's impossible to define, but because the material out there doesn't respect any single plane to begin with. If you could somehow travel far enough to reach it, you'd find roughly the same density of icy bodies, whether you approached from directly above the ecliptic, directly below it, or anywhere along it. A spherical halo, built from material likely flung outward from the flat inner disk billions of years ago by gravitational encounters with the giant planets, scattered into every direction until any trace of the original flat shape was erased entirely. The very existence of a spherical Oort cloud surrounding a flat planetary disk is, in its own way, a perfect illustration of everything this question turns on. Close to the Sun, gravity, collisions, and billions of years of settling produced almost perfect flatness. Far enough away, where interactions become rare and chaotic rather than constant and damping, that flatness breaks down entirely. And up simply stops being a meaningful direction at all. Getting back to the practical challenge of actually traveling perpendicular to the ecliptic, it helps to understand exactly why the cost is so steep in engineering terms, not just conceptually. Orbital mechanics has a well-known relationship for what's called a plane change maneuver, the technical term for altering the tilt of a spacecraft's orbit, rather than simply speeding it up or slowing it down. The energy required to change the angle of an orbit depends heavily on two things: how large that angle is, and how fast the spacecraft is already moving within its current orbit. For a spacecraft moving at Earth's orbital speed of about 18.5 miles per second, changing its orbital plane by a large angle costs enormously. Anything approaching a full 90-degree turn away from the ecliptic requires a change in velocity comparable to the orbital speed itself, not some small fraction of it. That's the counterintuitive part that trips up a lot of people encountering this for the first time. You might expect that turning to a new direction should cost less than traveling twice as fast in a straight line. But in orbital mechanics, changing direction at high orbital speed is often more expensive than changing speed by the same amount. You're not just adding motion, you're cancelling out a large existing motion in one direction while building up new motion in a completely different one. Both of those changes draw from the same limited fuel supply. This is precisely why mission planners so consistently choose small, gradual plane changes combined with gravity assists rather than one large maneuver. A small change in inclination, a few degrees here and there, achieved gradually using a planet's gravity at just the right moment during a flyby, costs comparatively little. A large change, the kind needed to go from riding along the ecliptic to climbing steeply above or below it, costs enormously more. That's exactly why Ulysses needed Jupiter's assistance to make its journey feasible, and why no other mission has attempted anything close to that scale of plane change since. Gravity assists themselves are worth understanding in a little more depth. They can seem almost magical at first glance, a spacecraft gaining speed or changing direction for free, seemingly without violating any law of physics. The trick is that nothing is actually free. Energy is simply being borrowed from the planet, doing the assisting. As a spacecraft approaches a large planet like Jupiter, the planet's gravity pulls it into a curved path. It accelerates as it falls toward the planet and decelerates by the same amount as it climbs back away. So, its speed relative to the planet itself is unchanged by the encounter. But relative to the Sun, something very different happens. If the spacecraft approaches from the right direction, trailing behind the planet's own motion around the Sun, it can pick up a portion of the planet's orbital velocity during the encounter. It borrows that momentum and leaves with more speed relative to the Sun than it arrived with. The planet, in turn, loses an infinitesimally small amount of its own orbital momentum in exchange. An amount so vanishingly tiny compared to a planet's enormous mass that it's completely undetectable. But real all the same, a genuine transfer of momentum from planet to spacecraft, governed by the same conservation laws that apply to every collision and near miss in physics. For missions traveling outward through the ecliptic, this exchange typically boosts speed and bends the trajectory sideways, staying roughly within the plane. Ulysses used Jupiter's gravity for something more dramatic. It approached at precisely the angle needed to bend its path, not sideways within the plane, but steeply out of it. Trading a modest amount of Jupiter's own vast orbital momentum for the kind of plane change that would have been essentially impossible to achieve through onboard propulsion alone. Ulysses wasn't the last word on studying the Sun from unusual angles, even if it remains the most extreme example. The European Space Agency's Solar Orbiter mission launched in February of 2020. It was designed with a more modest but still significant version of the same goal, gradually raising its orbital inclination relative to the ecliptic, using a series of gravity assists at Venus, rather than one dramatic encounter with Jupiter. Each Venus flyby nudges Solar Orbiter's inclination a little higher, building toward angles expected to reach the mid-20s by the end of its nominal mission, and as high as the low 30s during an extended mission phase. This will allow it to capture the first ever clear images of the Sun's polar regions. Something even Ulysses, with its extreme inclination, wasn't equipped to photograph directly, since it carried instruments built for measuring particles and magnetic fields rather than cameras. Solar Orbiter's approach shows the more common, practical version of climbing out of the plane. Not a single dramatic leap the way Ulysses achieved, but a patient, incremental climb. Repeated gravity assist after gravity assist, trading years of mission time for a plane change that would be far too expensive to attempt all at once. It's a reminder that even a modest amount of up in the solar system has to be earned gradually. Planet encounter by planet encounter, rather than simply pointed toward and flown to directly. Zoom back out from our own solar system's disk, and the same layered structure repeats itself on a staggeringly larger scale. The Milky Way galaxy is itself a flattened, rotating disk, for essentially the same reason our solar system is. An enormous cloud of gas that collapsed under its own gravity billions of years earlier. It conserved its angular momentum and flattened through countless internal collisions, exactly the way the much smaller solar nebula did later on. Our Sun sits embedded within one of the galaxy's spiral arms, a region sometimes called the Orion Arm or the local spur. It's roughly 26,000 light-years from the galaxy's center. That location places us well out from the crowded, energetic core and comfortably within the flattened disk of stars that makes up most of the galaxy's visible structure. From within that disk, Looking along its flattened plane, we see the dense band of stars we call the Milky Way, stretching across our night sky. It's the same edge on view of a flattened disk that ancient skywatchers unknowingly observed when they traced the ecliptic, just projected on an almost unimaginably larger scale. The Sun completes one full orbit around the galaxy's center, roughly every 230 million years. A span of time sometimes referred to informally as a galactic year. It's so enormous that the last time our solar system completed a full lap around the galaxy, the earliest dinosaurs had not yet appeared on Earth. Within that immense orbit, the Sun also drifts gently above and below the galactic plane. It oscillates with a period of roughly 30 million years from one extreme to the other, carried up and down by the combined gravitational pull of the galaxy's disk. That pull acts almost like an enormous, slow-motion restoring force, pulling the Sun back each time it strays too far from the plane's center. Some researchers have investigated whether this slow vertical rhythm might correlate with long-term patterns in Earth's geological and biological history. Passing through the denser regions near the galactic plane could theoretically increase exposure to interstellar material or cosmic radiation. Though this remains an active and unsettled area of research rather than an established fact, the evidence connecting it directly to specific events on Earth remains far from conclusive. What is well established is the underlying mechanism. The Sun genuinely does move up and down relative to the galaxy's own flattened disk on a slow, repeating, multi-million-year cycle, entirely independent of anything happening within our own solar system's much smaller, faster ecliptic plane. Stack all of these layers together, and the picture that emerges is almost dizzying in its complexity. Earth spins on its own axis, tilted about 23.4 degrees relative to its orbital plane around the Sun. That plane is the ecliptic, tilted a further 60 degrees or so relative to the plane of the Milky Way galaxy. The galaxy's own plane is itself oscillating slowly up and down relative to some larger reference defined by the distribution of mass across the wider cosmic neighborhood. All of it embedded within the vast web-like structure of galaxy clusters and filaments that makes up the largest scale structure of the observable universe. At every one of these scales, a local up exists, defined entirely by whatever rotating or clustering structure happens to dominate the surrounding gravity at that particular size. And at every one of these scales, that local up is completely unrelated to the one nested inside or outside it, tilted at its own unpredictable angle, inherited from its own separate history of formation. There is no thread connecting Earth's up to the solar system's, up to the galaxy's up. Each one had to be discovered, measured, and understood entirely on its own terms. Often centuries apart, by scientists working with completely different tools and completely different questions in mind. Bring all of that back down to the very specific, very human question this all started with. Why can't you go up in the solar system? It's worth putting exact numbers next to the comparison between escaping the solar system outward and climbing straight out of the plane. The gap between them is bigger than most people expect. A spacecraft sitting in Earth's orbit is already moving at about 18.5 miles per second relative to the Sun. It's carried along by the same orbital motion Earth itself has held for billions of years. To escape the Sun's gravity entirely, traveling outward and eventually leaving the solar system altogether, that spacecraft needs a velocity of about 26.4 miles per second relative to the Sun. That means its engines only need to add roughly 7.9 miles per second on top of the speed it already has. It's already moving in a useful direction and simply needs to go faster along that same path. That's a large but manageable number. Well, within what modern rockets, combined with a gravity assist or two along the way, have repeatedly demonstrated they can achieve. That's exactly how missions like Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons all became capable of eventually leaving the solar system. Now compare that to a spacecraft attempting to travel straight up out of the ecliptic instead. Rather than building on the 18.5 miles per second it already has, it needs to cancel almost all of it first. Only after that cancellation does upward motion become the spacecraft's dominant direction of travel. Cancelling 18.5 miles per second of existing velocity and then adding new velocity in a completely different direction on top of that adds up fast. The total delta V requirement runs well beyond the 7.9 miles per second needed to simply escape outward along the plane. In practical terms, a direct plane change of 90 degrees at Earth's orbital speed can require somewhere in the range of 26 miles per second of delta V, if attempted all at once. That's more than 3 times what's needed to leave the solar system entirely in the direction you're already moving. No chemical rocket system that has ever been built carries anywhere near enough propellant to deliver that much velocity change directly. Nor does anything engineers are seriously proposing to build with current technology. That's precisely why nobody has ever tried, and why Ulysses had to borrow the maneuver from Jupiter's gravity instead of attempting it with its own engines. This is also why upcoming and proposed propulsion technologies matter so much to the future of this particular problem. Chemical rockets have powered every crewed mission and the vast majority of robotic missions to date. They're extremely powerful over short bursts, but limited by how much propellant they can physically carry. Electric propulsion systems, often called ion engines, work completely differently. They produce a tiny amount of thrust, often no stronger than the push of a piece of paper resting in your hand. But they sustain that gentle push for months or even years at a time, using only a small amount of propellant compared to a chemical rocket delivering the same total velocity change. NASA's Dawn spacecraft studied the asteroid Vesta and the dwarf planet Ceres between 2007 and 2018. It used ion propulsion to accumulate a total velocity change of more than 24,000 miles per hour over the course of its mission. That's an amount that would have required an enormous, impractical quantity of chemical propellant to achieve directly. But ion engines managed it gradually, thrusting patiently for the majority of the mission's duration. Applying that same patient, low-thrust approach to a plane change maneuver is, at least in principle, one of the more promising paths toward eventually making a steep departure from the ecliptic more practical. Instead of trying to cancel 18.5 miles per second of velocity in one dramatic burn, an ion-powered spacecraft could chip away at that velocity change gradually over years. Using a small fraction of the propellant a chemical rocket would need for the same total maneuver. No mission has yet attempted a large-scale plane change, primarily through electric propulsion. But as ion engines and related technologies continue to mature, it remains one of the more realistic long-term paths toward eventually sending something further out of the ecliptic than Ulysses or Solar Orbiter ever managed, without needing another fortunate gravitational assist from Jupiter to make it possible. There's a subtler geometric detail worth understanding too. It explains exactly what direction, straight up, out of the solar system, would even point toward. If you were trying to describe it precisely, rather than just gesturing vaguely above the plane. Astronomers define two fixed points in the sky called the North Ecliptic Pole and the South Ecliptic Pole, the two directions exactly perpendicular to the ecliptic plane, the closest thing the solar system has to a formal up and down. The North Ecliptic Pole sits in the constellation Draco, the Dragon, a faint, sprawling constellation that winds across the northern sky. The South Ecliptic Pole sits in the constellation Dorado, the Swordfish, visible from the southern hemisphere. These points are almost never discussed outside of specialized astronomical contexts. Almost nothing in the solar system ever travels toward them. There are no planets there, no significant asteroid populations there, nothing to visit or study by heading in that specific direction. Only the thin, uniform backdrop of distant stars, and far beyond them, other galaxies. If a spacecraft ever did manage to travel directly toward the North Ecliptic Pole, climbing straight up and away from the solar system's disk, it would eventually leave behind more than just the planets. It would leave the asteroid belt, the Kuiper belt, and even most of the flattened structure of dust and debris that fills the inner solar system. It would emerge into what is, from our perspective, remarkably empty space. That would offer an unobstructed view down onto the solar system's disk from above. The same way you might look straight down onto a spinning record from directly overhead. No spacecraft has ever traveled far enough in that specific direction to achieve that view directly. Though Ulysses came the closest of anything ever built. Its trajectory carried it to a maximum ecliptic latitude of a little over 80 degrees during its closest passes over the sun's poles. Tantalizingly close to true 90-degree, straight up, but still just short of it. Dictated by the specific geometry Jupiter's gravity was able to provide. It's worth taking a moment to appreciate just how much of the solar system's material structure remains crowded into that thin, flattened band. It underlines exactly why nearly every mission ever flown has had good reason to stay close to it. The asteroid belt sits between the orbits of Mars and Jupiter. It contains the overwhelming majority of the solar system's known asteroids, virtually all of them orbiting within a few degrees of the ecliptic plane. They're remnants of the same flattened disk that never managed to gather into a full planet, kept stirred up and prevented from doing so by Jupiter's powerful disruptive gravity nearby. Jupiter's Trojan asteroids are trapped in stable gravitational pockets 60 degrees ahead of and behind the planet in its orbit. They also sit almost precisely within the ecliptic, sharing Jupiter's own orbital plane closely enough that they represent yet another population of material a mission can potentially study along the way, simply by virtue of staying within the plane. Comets that originate from the Kuiper belt, the so-called short-period comets, return to the inner solar system on predictable, relatively frequent schedules. They also tend to orbit close to the ecliptic, inheriting that flatness from the same disc-shaped region they formed within. Every one of these populations, planets, asteroids, short-period comets, represents scientifically valuable material. A mission can encounter it more or less for free, simply by traveling within the plane it already needs to be in for efficient propulsion reasons. Leaving the plane means leaving nearly all of that behind. It means trading access to this rich, well-populated band of material for a view of empty space above and below it. That's a trade that has to be scientifically justified, and historically only Ulysses, and now gradually Solar Orbiter, have made that specific case successfully to mission planners and funding agencies. Step back far enough, past the solar system, past even the Milky Way's own flattened disk, and the entire concept of a preferred plane, a preferred up, starts to dissolve into something much stranger. Our galaxy is not alone in space. It's part of a loose collection of dozens of nearby galaxies called the local group, dominated by the Milky Way and the slightly larger Andromeda galaxy, both surrounded by dozens of smaller companion galaxies, all bound together by their mutual gravity, all moving through space together as a rough cluster. The local group itself is part of something much larger, a vast, sprawling collection of galaxy clusters called the Laniakea supercluster, a name that means immense heaven in Hawaiian. It was mapped in detail only within the last decade or so, by tracing the subtle flows of galaxies as they're gravitationally pulled toward a massive concentration of matter at the supercluster's center. Laniakea itself contains roughly 100,000 galaxies. It's spread across a region so large that light takes more than 500 million years to cross it. And even Laniakea isn't the end of the structure. On the largest scales, astronomers have been able to map. Galaxies and galaxy clusters aren't scattered randomly through space. They're arranged into a vast, web-like pattern, often called the cosmic web. Long filaments of galaxies and dark matter stretching across hundreds of millions of light years. Connected at dense nodes and separated by enormous, nearly empty regions called cosmic voids. At this scale, the idea of a single preferred plane, a single up or down, simply stops applying in any meaningful way. There's no galactic disk to be perpendicular to anymore. No single dominant rotating structure whose gravity defines a shared direction for everything nearby. Instead, there's a sprawling, three-dimensional lattice of matter, with no natural top, no natural bottom, no direction more special than any other. This connects to one of the deepest findings in modern cosmology. The observation that the universe, on its very largest scales, appears remarkably uniform in every direction, a property scientists call isotropy. The cosmic microwave background is the faint afterglow of light released roughly 380,000 years after the earliest moments of the universe. It has been mapped with extraordinary precision by space telescopes. It looks almost identical no matter which direction you look, varying in temperature by only a few parts in 100,000 across the entire sky. That uniformity is powerful evidence that the universe doesn't have a center, doesn't have an edge, and doesn't have a preferred direction built into its fundamental structure. Every location, every direction, appears statistically equivalent to every other, at least when you average out enough of it. That's about as far from Earth's simple, gravity-defined sense of up as you can possibly get. A universe where, ultimately, there is no true up at all. Only an endless series of local ups nested inside each other. Each one borrowed temporarily from whatever rotating disk, orbiting planet, or clustering mass happens to dominate the gravity in that particular corner of space. Bring that back, one final time, to the very grounded, very human question sitting underneath all of this. You wake up tomorrow morning, you stand up out of bed, and without even thinking about it, you know exactly which way is up. That knowledge feels absolute, permanent, built into the universe itself. It isn't. It's a temporary local agreement, negotiated between your body and the nearest large mass, in this case, Earth. Valid only as long as you remain close enough to Earth for its gravity to dominate everything else. Travel far enough away, and that agreement dissolves. It's replaced first by the confusing, directionless experience of freefall. Then, if you travel far enough and fast enough, by an entirely different up, defined not by Earth anymore, but by the flattened disk of the solar system itself. An up so expensive to actually travel toward that in more than 60 years of spaceflight, humanity has only ever managed to send one machine seriously chasing after it. There's one more piece of orbital mechanics that explains why Ulysses's route through Jupiter wasn't just a clever trick. It was close to the only sensible option physics actually offered. Plane change maneuvers aren't equally expensive everywhere along an orbit. They're cheapest at the point in an orbit where a spacecraft is moving the slowest, and most expensive where it's moving the fastest. Near the Sun, a spacecraft moves quickly, since gravity accelerates anything falling deeper into a gravitational well. Earth, orbiting relatively close to the Sun, moves at that brisk 18.5 miles per second. Far from the Sun, out near Jupiter's orbit, roughly 5 times farther from the Sun than Earth is, a spacecraft naturally slows down considerably. It coasts along at only about 8 miles per second, rather than 18.5. Since the cost of a plane change scales directly with how fast you're already moving, performing that same 90-degree turn out near Jupiter's distance costs dramatically less than attempting it back near Earth's orbit, even before factoring in any assistance from Jupiter's gravity at all. This is exactly why Ulysses's route made sense as a two-step process rather than one direct maneuver. First, travel outward to Jupiter's distance, where the spacecraft's own orbital speed has already dropped considerably simply by virtue of being farther from the Sun. Second, once out there, use Jupiter's own gravity for the final, dramatic bend out of the plane. That maneuver was already cheaper simply because of where it was happening, and then made dramatically cheaper still by borrowing momentum from the planet itself. Layer these two effects together. Slower orbital speed at greater distance, plus a gravity assist precisely timed and angled to bend the trajectory out of the plane. That's what finally brought an otherwise impossible maneuver down into the range of what an actual spacecraft, with an actual limited fuel supply, could realistically achieve. It's worth briefly contrasting this against a very different, much more recent mission that also studies the Sun up close, but takes an entirely different approach to getting there. NASA's Parker Solar Probe launched in August of 2018. It was built to fly closer to the Sun than any spacecraft in history. It eventually passed within about 3.8 million miles of the Sun's surface, well inside the orbit of Mercury. Close enough to directly sample the Sun's outer atmosphere, the corona, for the first time. Getting that close required an enormous amount of orbital energy to shed. A spacecraft, launched from Earth, actually starts out with too much sideways orbital velocity to simply fall toward the Sun. That same inherited 18.5 miles per second that makes leaving the ecliptic so difficult also works against falling straight inward toward the Sun. For very similar reasons, cancelling sideways motion is expensive, no matter which direction you're trying to redirect it toward. Parker Solar Probe solved this not by leaving the ecliptic, but by staying within it. It used repeated gravity assists at Venus, 7 flybys spread out over roughly 7 years. Each one trimmed away a little more of that troublesome sideways velocity, gradually shrinking and tightening its orbit closer and closer to the Sun with each pass. Parker's mission and Ulysses's mission make an interesting pair. They tackle two entirely different, equally difficult problems using the exact same underlying tool, the gravity assist, but aimed in completely different directions. Ulysses needed to escape the ecliptic plane entirely, climbing up and away from it using Jupiter's gravity. Parker needed to stay within the ecliptic, but shed enormous amounts of sideways velocity to fall closer to the Sun, using repeated assists at Venus instead. Neither problem could be solved with brute force propulsion alone. Both stand as reminders that in orbital mechanics, the most extreme destinations, whether that's straight up out of the plane or straight down toward the Sun, almost always require patient, borrowed momentum rather than raw engine power. All of this technical detail eventually circles back to a simple, almost overlooked truth about what up really costs. Not just in fuel, but in mission design. In years of patient planning. In entire careers spent working out exactly which planet could offer the right nudge. At exactly which point in its orbit. In exactly the right direction. Every mission that has ever meaningfully challenged the ecliptic plane has done so the same way. Ulysses climbing over the Sun's poles. Solar Orbiter gradually raising its own inclination using Venus. Parker Solar Probe shedding velocity to dive toward the Sun's corona. Each one treats the solar system's planets not as destinations in themselves, but as gravitational tools. Precisely timed favors, borrowed from worlds that happen to be in the right place, doing the work no rocket alone could afford to do. There's a very different, much more human dimension to this question too. One that has nothing to do with trajectories or delta V calculations at all. It has everything to do with what up and down might mean for people actually living and working in space over long periods of time, rather than for a robotic probe passing through on its way somewhere else. Humanity may eventually build long-term habitats in space, in orbit around Earth, out near the Moon, or eventually farther afield. The disorienting, weightless free-fall experienced aboard the International Space Station today probably won't be the long-term answer. Extended weightlessness causes real, well-documented harm to the human body. Loss of bone density, loss of muscle mass, changes to fluid distribution and vision. Current astronauts manage these effects through rigorous daily exercise routines, but longer missions may need to address them more fundamentally. The most commonly proposed long-term solution isn't exercise at all. It's rotation. Spinning a habitat or an entire spacecraft slowly around a central axis. The resulting outward force, technically not gravity at all, but something called centripetal effect, pushes occupants toward the outer walls of the structure with a force that feels remarkably like the pull of gravity itself. In a rotating habitat, up and down return, but they're redefined entirely. Down becomes outward, away from the central axis of rotation, toward the rim of the spinning structure. Up becomes inward, toward the center. That's the one place in a rotating habitat where the sensation of weight would shrink toward nothing at all, since the center of rotation is the one point barely moving at all compared to the spinning rim around it. Engineers and researchers have studied various concepts for structures like this for decades. From early theoretical proposals in the mid-1900s, envisioning giant rotating wheel-shaped stations, to more recent, more modest concepts explored by space agencies and private companies alike. They've tested how large a rotating structure would need to be, and how fast it would need to spin, to produce a comfortable, Earth-like sense of down without making occupants dizzy or nauseated. Spin too fast, or build the habitat too small, and the difference in centripetal force between someone's head and someone's feet becomes noticeable and uncomfortable, an effect sometimes called The gravity gradient, essentially a milder version of the same physics that produces tides. It distorts the smooth, consistent sense of down that we're used to on a planet as large as Earth. Build the habitat large enough and spin it slowly enough, and that gradient becomes small enough to be unnoticeable. It produces an artificial down, indistinguishable, in everyday experience, from the real thing. This matters directly to the question of up and down in space. It demonstrates something important, that up doesn't strictly require a planet at all. It requires a consistent force, pointing in a consistent direction. Strong enough for your body's three separate orientation systems, your inner ear, your eyes, and your pressure-sensitive nerves, to agree on once again. Planetary gravity is simply the most familiar, most abundant source of that force. But it isn't the only possible one. A rotating structure can manufacture its own local up and down, entirely independent of any nearby planet, star, or galaxy. Defined purely by its own spin, rather than by any external gravity at all. In a strange way, this is the most literal, most controllable version of creating up that humanity has ever seriously worked toward. Not by traveling to some cosmic direction that happens to be labeled up. By building a structure that manufactures its own local sense of it, wherever in space that structure happens to be. It's a useful reminder of everything. This entire question has been circling around from the very beginning. Up was never really about a direction in space at all. It was always about force. About something pulling consistently enough, strongly enough, and steadily enough that your body could build an entire, unquestioned sense of orientation around it. On Earth, that force is gravity, pulling toward the planet's center. That's the up you've relied on your entire life without a second thought. In the solar system at large, the closest equivalent isn't a force pulling you anywhere in particular. It's the shared orbital motion nearly everything inherited from the same flattened disk of gas and dust the sun and planets were born from. That motion is so deeply built into the structure of the solar system that fighting against it, climbing away from the plane it defines, remains one of the single most expensive things any spacecraft can attempt. And in a rotating space habitat, that force would come from something else again. The structure's own spin, manufacturing an artificial down out of nothing but rotation and geometry. Three completely different sources. Three completely different versions of up. All of them local. All of them borrowed, in one way or another, from whatever happens to be spinning, orbiting, or pulling nearby. Everything described so far has treated the solar system's flatness as if it was simply the way things have to be. The natural, expected result of a rotating cloud collapsing under gravity. For most of the history of astronomy, that assumption seemed safe. Our own solar system was the only detailed example anyone had to study. Then, astronomers started actually watching other star systems form, and later, watching fully formed planetary systems around other stars. The assumption held up remarkably well, almost everywhere they looked. In 2014, radio telescopes captured one of the clearest images ever taken of a young star system still in the process of forming. A star called H.L. Tauri, roughly 450 light-years away. It was surrounded by a glowing disk of gas and dust with distinct, concentric gaps carved into it, thought to be the early footprints of planets still gathering material along their own orbits. The disk was flat, just like the one that built our own solar system billions of years earlier. It offered direct visual confirmation of a process astronomers had only been able to infer indirectly before. Similar disks have since been imaged around other young stars. Each one reinforces the same basic picture. Flat, rotating disks are simply the ordinary, expected outcome whenever a star and its planets are being built from a collapsing cloud of gas. But in 2025, a discovery emerged that complicated this tidy picture in a genuinely surprising way. Astronomers using the European Southern Observatory's Very Large Telescope in Chile had been carefully studying a pair of small, dim objects called brown dwarfs. Bodies too large to be classified as planets, but too small to sustain the nuclear fusion that defines a true star. They orbit each other closely as what's known as an eclipsing binary, a system where each object periodically passes in front of the other as seen from Earth. While refining measurements of the pair's orbit, the research team noticed something they weren't looking for. Small, unexplained wobbles in the brown dwarf's motion that couldn't be accounted for by the two objects' gravity alone. After testing every plausible explanation, only one scenario fit the data: the presence of a third body, a planet. And not one orbiting in the same flat plane as the two brown dwarfs, the way nearly every other planet found around a binary star system before it had. This planet, designated 2M1510 ABB, was orbiting nearly perpendicular to its two host bodies, tracing a steep polar path around the pair, rather than the flat, in plane orbit astronomers had come to expect. It marked the first confirmed case of a planet locked into a genuinely polar orbit around a pair of stars. Proof that theoretical predictions researchers had floated for years actually play out in nature, not just on paper. The discovery came as a considerable surprise, even to the astronomers involved. The observations that revealed it were never designed to search for anything of the kind. The planet's existence only became apparent as an unavoidable conclusion once every simpler explanation had been ruled out. What makes 2M1510 ABB so striking is that it represents a real, observed example of exactly the kind of up this whole exploration has been discovering is so difficult to reach within our own solar system. Somewhere else in the galaxy, an entire planet is doing, permanently and stably, the very thing that has cost humanity's space program the most. More energy, more mission planning, more borrowed gravity from Jupiter than almost anything else we've ever attempted. It's quietly orbiting its two host stars from directly above and below their shared plane, rather than riding alongside it the way nearly every other known planet does. It's a reminder that the physics making a polar path so expensive to reach from within our own solar system doesn't forbid such paths from existing at all. It simply means that reaching one, starting from deep inside a flat, already spinning disk the way Earth is, takes an extraordinary amount of borrowed energy. A planet forming under different circumstances, in a different kind of system, might never have needed to spend that energy in the first place. There's a smaller, closer to home example of planetary paths bending away from the ordinary plane. It shows just how rare and hard even a modest departure from flatness really is, even for our most celebrated missions. Voyager 2's famous grand tour of the outer solar system visited Jupiter, Saturn, Uranus, and Neptune between 1979 and 1989. It was made possible by an alignment of the four giant planets that occurs only once every 176 years or so. The planets were positioned in such a way that a single spacecraft could use each one's gravity to bend its path onward to the next. It gained speed and adjusted direction with each flyby, rather than needing separate rockets and separate launches for each destination. Even that, extraordinary, once in over a century, alignment kept Voyager 2 relatively close to the ecliptic plane throughout its entire outer solar system tour. Each gravity assist nudged its trajectory sideways and outward, far more than it ever nudged it up or down. Both Voyager spacecraft famously carry a golden record on board. A phonograph disc containing sounds, images, and music intended to represent life and culture on Earth. It was included in case either spacecraft is ever recovered by another civilization somewhere in the vast reaches of interstellar space they're now traveling through. That inclusion says something quietly moving about the missions themselves. Even as they were designed around the coldest, most exacting orbital mechanics imaginable, threading gravity assists through a precise alignment of planets, there was still room for one more thing. A message meant for someone, or something, that might never receive it. Both Voyagers are now well beyond the orbit of Pluto. They're traveling through the outermost fringes of the solar system, headed generally outward along paths still shaped, even this many decades later, by the flat plane and the borrowed planetary gravity that first sent them on their way. Taken together, all of this builds toward the same underlying lesson from a dozen different angles. The physics of the flattened disk. The razor-thin margin by which Ulysses managed its climb over the sun's poles. Solar Orbiter's patient, incremental version of the same feat. Parker Solar Probe's mirror image challenge of falling inward rather than climbing outward. And now, a planet somewhere else in the galaxy, quietly living out the polar orbit our own missions have found so punishingly difficult to reach. Up was never a simple, universal direction waiting out there to be flown toward. It's a direction defined entirely by whatever gravity, whatever rotation, whatever inherited motion happens to dominate the particular patch of space you're standing in, or falling through, or orbiting around at any given moment. Change the scale, and the direction changes with it. Sometimes gently, sometimes so completely that the up you knew a moment ago stops meaning anything at all in the new context you've entered. Something here might seem to contradict everything covered so far. At a smaller scale, going up is actually something we do all the time, routinely, without any of the drama attached to leaving the ecliptic plane. Earth orbit is full of satellites that travel in what are called polar orbits, paths that carry them almost directly over Earth's north and south poles, instead of following the planet's equator the way many communications satellites do. Weather satellites, many spy satellites, and a large share of Earth observation satellites deliberately choose these polar paths. As the satellite circles from pole to pole, Earth slowly rotates underneath it. That lets the satellite eventually scan the entire surface of the planet, strip by strip, over the course of many orbits. Something an equatorial satellite, permanently tracking the same band around the planet, could never manage on its own. This might sound like exactly the same kind of maneuver that made Ulysses's mission so difficult. Deliberately choosing a path perpendicular to a planet's natural rotational plane. And in a sense, it is. But the scale involved makes all the difference in the world. Earth's own equatorial rotational speed is only about 0.29 miles per second, a small fraction of the 18.5 miles per second Earth carries around the Sun. Reaching low Earth orbit at all requires roughly 4.9 miles per second of orbital velocity. Shifting that orbit's inclination from equatorial to polar costs considerably less than shifting a solar orbit's inclination by the same 90 degrees. The underlying speeds involved, and therefore the momentum that has to be cancelled and rebuilt, are so much smaller to begin with. That's why polar orbiting satellites are common, launched routinely from sites specifically chosen to make reaching such orbits efficient, while a polar orbit around the Sun itself remains something only one mission in history has ever seriously attempted. The same underlying rule applies at every scale. Changing a plane is expensive in proportion to how fast you're already moving within the plane you're trying to leave. At Earth's modest rotational and orbital speeds close to home, that expense is manageable. It simply isn't manageable once you're contending with the Sun's far larger gravitational grip and the far higher orbital speeds that come with it. The International Space Station itself orbits at an inclination of about 51.6 degrees relative to Earth's equator. That's a compromise, chosen specifically so that spacecraft launching from both American and Russian launch sites at their respective latitudes could each reach the station efficiently. A reminder that even here, close to home, the specific angle of an orbit is never arbitrary. It's always the result of careful calculation, weighing cost against purpose. A similar story of plane and angle plays out with the Moon. It explains something that puzzles a lot of people the first time they think carefully about it. If the Moon orbits Earth and Earth orbits the Sun, why doesn't a solar eclipse happen every single month, every time the Moon passes between Earth and the Sun? The answer is, once again, a matter of planes not quite lining up. The Moon's orbit around Earth is tilted by about 5.1 degrees relative to the ecliptic. The plane Earth itself traces around the Sun. That's a small angle. But it's enough that most months, when the Moon passes roughly between Earth and the Sun, it actually passes slightly above or slightly below the Sun in our sky, rather than directly in front of it. That means it misses the precise alignment needed to cast a shadow anywhere on Earth's surface. Only twice within each of the Moon's orbits does its path actually cross the ecliptic plane exactly. At 2 points, called the ascending node and the descending node. Only if the Moon happens to be new or full, at almost exactly the moment it's passing through one of those two crossing points, do we get an eclipse at all. A solar eclipse if the Moon is new and directly between Earth and the Sun. A lunar eclipse if the Moon is full and directly on the opposite side of Earth from the Sun. This is why eclipses come in predictable but limited windows called eclipse seasons, roughly twice a year rather than happening every single month. It's a small, elegant example of the same underlying idea running through everything else here. Even a modest few degrees of tilt between two orbital planes is enough to turn what could have been a routine, monthly event into something comparatively rare, dependent on the precise timing of when two slightly misaligned paths happen to cross. Saturn offers one more vivid, visible example of orbital planes and their consequences. One you can actually observe for yourself with a modest telescope over the span of years. Saturn's magnificent rings orbit directly in the plane of the planet's own equator, tilted about 26.7 degrees relative to Saturn's own orbital path around the Sun. As Saturn slowly makes its way around the Sun, a journey that takes about 29.5 years to complete, that fixed tilt keeps changing how the rings look from Earth. They present themselves to us here at a constantly changing angle, appearing wide open and spectacular for years at a time, then gradually narrowing. Eventually, roughly every 15 years, they appear to vanish almost entirely as the rings turn edge onto our line of sight. They're so thin, relative to their enormous diameter that they briefly seem to disappear from view entirely in all but the most powerful telescopes. That ring plane crossing is a striking, direct demonstration of something important. A ring system, or any orbiting structure, only looks flat and impressive from certain angles. From directly along its own plane, it reveals just how astonishingly thin it actually is. A razor edge of ice and rock stretching across hundreds of thousands of miles, but rising, at most, only a few dozen feet thick in most places. It's a small, visible echo of the entire solar system's own structure. A flat, thin disk that looks completely different depending on how you view it. Broadside, the way we mostly picture the solar system in illustrations, or edge-on, the way ancient skywatchers actually experienced it every time they traced the narrow band of the zodiac across their night sky. Without ever quite realizing, they were looking at the planet's spinning disk from the inside, along its own thin edge. All of these examples exist at wildly different scales. Satellites, choosing between equatorial and polar paths around Earth. The Moon's slightly tilted orbit, deciding when eclipses can occur. Saturn's rings, revealing their true thinness only when viewed edge-on. But they're all versions of the exact same underlying geometry. A flat, rotating structure only stays flat because something forced it flat in the first place. Angular momentum, collisions, gravitational settling, moving away from that flatness, climbing up, relative to whatever plane you started in, always costs something. Whether that cost is a satellite needing a slightly more expensive launch trajectory, or an entire spacecraft needing to borrow momentum from the largest planet in the solar system just to manage a fraction of the climb. The idea of manufacturing artificial gravity through rotation has a surprisingly long history. Tracing that history shows how consistently engineers have returned to the same basic solution whenever they've seriously grappled with what long-term life away from Earth's gravity would actually require. In the 1920s, one of the earliest detailed proposals for a rotating space station came from a Slovenian engineer named Herman Potočnik. He wrote under the pen name Herman Nordung. He described a wheel-shaped station, spinning slowly enough to generate a comfortable sense of weight along its outer rim, an idea that was almost entirely theoretical at the time, decades before any nation had the rocketry needed to put anything into orbit at all. The concept resurfaced prominently in the 1950s. Rocket engineer Wernher von Braun was working on early conceptual designs for American space exploration. He popularized a similar wheel-shaped rotating station in a series of widely read magazine articles and television programs. He imagined a station roughly 250 feet across, spinning to produce a sense of gravity for a crew, intended to use it as a staging point for future missions to the Moon and beyond. That wheel-shaped silhouette became so culturally embedded that it went on to appear in science fiction for decades afterward. It shaped public imagination about what space stations would eventually look like. But the space stations actually built and flown, from Skylab in the 1970s through Mir and the International Space Station in the decades since, have all been non-rotating, free-falling structures instead. Largely because building and safely spinning a large station remains a far more complex engineering challenge than assembling a stable, non-rotating one. In the 1970s, physicist Gerard O'Neill expanded the concept considerably further. He proposed enormous rotating cylindrical habitats, miles long, spinning to produce Earth-like gravity along their inner surface. They were envisioned as full-scale space colonies, capable of housing tens of thousands of people, complete with simulated weather, agriculture, and daylight, produced by mirrors reflecting sunlight in through the cylinder's length. O'Neill's designs remain influential today. They're studied and referenced by space agencies and private companies alike as a template for what permanent, large-scale space habitation might eventually look like. Nothing built at that scale has ever left the drawing board, though. Not because of the physics, which is reasonably well understood, but because of the sheer scale of material and construction such structures would require, likely drawing on resources mined directly from the Moon or from asteroids, rather than launched at great expense from Earth's own surface. What's consistent across a full century of these proposals, from Nordung's early wheel in the 1920s to modern studies still being conducted today, is the underlying physical principle. In the absence of a planet's gravity, rotation is the most straightforward, most thoroughly understood way to manufacture a substitute, converting spin into an outward push that stands in for the pull we're evolved to expect. It's a quiet reminder that even as humanity dreams up increasingly ambitious visions of permanent life away from Earth, the solution to recreating down keeps circling back to the same basic idea. The alternative, living out an entire life in the kind of directionless free-fall astronauts currently experience aboard the International Space Station, carries real, measurable costs to the human body. Costs that no amount of daily exercise fully offsets over years rather than months. There's something clarifying about following this question as far as it goes. From the simple, unquestioned certainty of standing on solid ground through the disorientation of freefall. Through the flattened disk that shaped the entire architecture of our solar system, out to the razor-thin margin by which a single spacecraft once managed to climb above and below the sun's poles. And finally out to the discovery, somewhere else entirely in the galaxy, of a planet quietly living out an orbit our own missions have found almost prohibitively difficult to reach. At no point along that journey does Up stop existing. It just keeps changing what it's borrowed from. Standing on Earth, Up is borrowed from the planet beneath your feet. A direction so reliable, you've never had reason to question it. Standing, hypothetically, on a hull somewhere in the depths of the solar system, Up would be borrowed from the flattened disk every planet, asteroid, and comet still respects. A direction so expensive to actually travel toward that reaching it has occupied entire careers, entire missions, entire decades of careful trajectory planning. And standing, hypothetically again, somewhere near a pair of brown dwarfs 20 some light years away, on the surface of a planet like 2M 1510 ABB. Up and down might mean something else again, entirely. A direction so different from our own solar system's version of flat that it took astronomers completely by surprise the moment they finally found unmistakable evidence for it. None of this makes Up any less real. If anything, it makes the version of Up you rely on every single day feel more remarkable, not less. Once you understand how much it actually depends on, how many billions of years of cosmic history had to unfold in exactly the right sequence. A cloud collapsing, a disk flattening, a planet condensing in exactly the right place, a moon forming to stabilize that planet's tilt. All of it just for the simple, reliable sense of Up you feel standing in your own home tonight to exist at all. It's not a universal fact handed down by the structure of space itself. It's a local gift, produced by the specific arrangement of matter and motion happening to surround you right now, valid for exactly as long as you remain within its reach. Utterly different from the version of up waiting, just beyond it, in every direction, at every scale, all the way out to the edge of what we've managed to observe. There's one last piece of evidence for the solar system's flatness that you can actually see with your own eyes. Without a telescope, a spacecraft, or a single equation, if you know when and where to look, it's called zodiacal light. A faint, softly glowing band visible just after sunset or just before sunrise, under dark skies far from city lights. It stretches upward from the horizon, along the same narrow band ancient sky watchers once traced across the zodiac. That glow isn't starlight, and it isn't light from the sun scattering through Earth's own atmosphere the way a sunset does. It's sunlight reflecting off countless tiny particles of interplanetary dust, the leftover debris of collisions between asteroids and the slow disintegration of comets as they pass near the sun. That dust is spread thinly across the entire inner solar system, but concentrated most densely exactly where you'd expect, within the same flat plane every planet orbits in. Because that dust is so thoroughly confined to the ecliptic, the reflected sunlight it produces appears in the sky as a narrow, tilted band, rather than a general haze spread evenly overhead. A direct, visible echo of the same disc-shaped structure responsible for planetary orbits, asteroid orbits, and the very reason climbing straight out of that structure costs more energy than leaving the solar system outward along it. Some cultures historically referred to this glow as a false dawn, a soft light appearing before actual sunrise, easily mistaken for the first hint of morning by anyone unfamiliar with it. It was really only well studied and correctly explained as sunlight scattered by interplanetary dust, starting in the 1800s and 1900s. Once astronomers had the tools to separate it clearly from other sources of faint night sky glow. Standing under a genuinely dark sky, watching that pale, tilted column of light rise from the horizon, you're looking directly along the plane of the solar system itself. You're tracing with your own eyes the exact flattened structure this entire exploration has been circling around from the very beginning. The same structure that makes going sideways, outward, planet to planet, so much more achievable than going straight up. The same structure that turned one single mission, climbing briefly above and below it decades ago, into one of the more remarkable feats in the entire history of spaceflight. It's a small, quiet, entirely visible reminder that the flatness of the solar system isn't an abstract idea confined to diagrams and orbital mechanics textbooks. It's sitting right there in the sky, faint but real, every single clear night. For anyone patient enough and far enough from artificial light to actually look for it. There's a small, almost poetic detail that captures just how unfamiliar the solar system's own version of up really is, especially compared to the version of up we've built centuries of navigation and storytelling around. Nearly everyone has heard of Polaris, the North Star. It sits almost exactly above Earth's North Pole, along the extension of Earth's own rotational axis. That's why it appears to stay nearly fixed in the sky, while every other star wheels slowly around it over the course of a night. Polaris earned its fame honestly. It's been used for navigation for centuries, precisely because Earth's axis happens to currently point toward a reasonably bright, easy-to-identify star. That's a fortunate coincidence of timing. Earth's axis actually wobbles slowly over a cycle of about 26,000 years. Polaris hasn't always held that position, and won't hold it forever either. The North Ecliptic Pole, the true up of the solar system's own disk, rather than Earth's daily spin, enjoys no such convenient marker. sitting quietly within the faint constellation Draco. That point in the sky isn't marked by any bright, easily recognized star at all. Nothing a sailor could have steered by. Nothing that made its way into ancient mythology as a fixed point of reference the way Polaris did. It's a direction defined purely by calculation, by careful geometry, rather than by any convenient beacon happening to sit there. In a way, that absence says as much about how unfamiliar the solar system's true up really is as anything else covered tonight. Earth's up came with its own guide star, bright and useful, built into the culture and navigation of nearly every civilization that ever looked up at the night sky. The solar system's up came with nothing. No star, no landmark, no ancient name. Just an empty, unremarkable patch of sky that only became meaningful once astronomers worked out precisely where the ecliptic plane's perpendicular actually pointed. Centuries after Polaris had already earned its place in nearly every culture's sky lore. It's worth ending with where this all might be headed next, because the story of up in the solar system is very much still being written. Mission planners and scientists have continued to study proposals for a more capable successor to Ulysses. One carrying cameras and imaging instruments Ulysses never had, hoping to actually photograph the sun's poles directly rather than only measuring the particles and magnetic fields passing through them. Every version of that proposal keeps running into the same wall this entire exploration has been circling around. The sheer cost of achieving a steep plane change, and every version keeps arriving at some variation of the same answer Ulysses and Solar Orbiter already settled on. Patient, repeated gravity assists, borrowing momentum, a little at a time from whichever planet happens to offer the most useful angle, rather than any dream of a single, direct, brute force climb straight out of the plane. That pattern is likely to continue for a long time yet. The underlying physics isn't going anywhere. Chemical rockets aren't getting dramatically more efficient at storing raw energy. And the 18.5 miles per second of inherited orbital velocity every mission launched from Earth carries with it isn't going to become any cheaper to cancel, just because the engineering around it keeps improving in other ways. What will most likely change, gradually, is the efficiency of low-thrust propulsion. Electric engines refined further, solar sails maturing into something more than an experimental technology, each one chipping away a little more cheaply at the enormous cost of a serious plane change. The same way, ion engines already made missions like Dawn possible, in ways chemical rockets alone never could have managed on the same budget. Someday, perhaps decades from now, a spacecraft may finally manage to climb higher above the ecliptic than Ulysses ever did, carrying instruments capable of finally showing us, directly and visually, what the sun's poles actually look like, rather than only what they measure. Until that day arrives, the record set by one spacecraft, launched in 1990, remains the closest humanity has ever come to actually going up. It borrowed its way past Jupiter to spend a handful of years looking down on the solar system from an angle almost nothing else has ever managed to reach. Thank you for joining me tonight on this exploration of a direction most of us never think to question. We've looked at where up and down actually come from. We've looked at why the solar system flattened into a disk in the first place. We've looked at why escaping that disk costs more energy than leaving the solar system altogether. And we've looked at why Ulysses remains the only spacecraft ever built specifically to make that climb. If this changed the way you think about the sky the next time you look up at it, take a moment to like this video and subscribe to the channel. It helps this channel reach more curious minds like yours. And remember, the next time someone asks you which way is up, the honest answer is that it depends entirely on what happens to be nearby, pulling on you, shaping the space around you, deciding, for that one local patch of the universe, which direction gets to be called up at all. Up, down, every direction we've ever trusted. All of it borrowed, never owned. Good night.